Hi, everyone. Welcome to Ask a Scientist. Today, we're going to be, my name is Carmen Lee, and I'm a PhD student at McMaster University in the Department of Physics and Astronomy. And to put that into school terms, I'm in about grade 20 of school. And today we're going to be talking a little bit about what I love, which is liquid solids and the squishy gooey things in between. And I got some really good questions about these topics. So hopefully you'll learn a lot and you'll be able to take home some information. Okay, so the first question that I got was from KN, and they asked, what do liquid, solid, and gas have in common? And I thought this was a really good question to start off with. So we're all familiar with liquids, gases, and solids, and what they have in common is that they're made of matter. And matter is stuff that we interact with every day that we can touch. So I'm made of matter, you're made of matter, the air we touch is made out of matter, and the liquid that we can drink is made out of matter. Everything we can touch. And so these three states of matter, what's interesting is that we can move from one state to the other. So solids, we can talk about solids. Solids are objects that stay the same shape, but if we just leave them alone. So this cup that I have is a solid because it stays in the shape of a cup. It doesn't change shape. But if I was to take, so another example, a good example is if I put an ice cube into a water bottle, that ice cube will stay the shape of an ice cube. It won't take the shape of the water bottle. However, if we leave that ice cube out at room temperature long enough, it's going to melt and turn into liquid water. And that water, one of the characteristics of it is that it will flow and take the shape of the container that it's in, so in this case, the water bottle. Now, if we keep heating up that water, it's going to eventually turn into water vapor, and that's in the gaseous phase. So if I were to hold that water bottle, it won't just full of gaseous water vapor, it wouldn't just stay in the shape of the bottle, it would in fact take on the whole shape of the whole container. So it won't just stay in the bottom. And the reason that these all have different properties is because of how the atoms or molecules are arranged inside of the state of matter. So we're on gas right now, but so if we were to start with a solid, the atoms or molecules are very tightly packed together, and they're bonded together so they can only wiggle around and they can't move past each other. However, in the liquid phase, these atoms and molecules are able to move and flow around each other. So that's why it can flow to take the shape of the container, where the atoms are stuck. In the gas phase, you can see that there's a whole bunch more space in between all those atoms, and they're able to move around much more quickly. And we'll talk a little bit later on about why we can move from those three states, why those three states matter, or how to get from those three states to each other. And the way that we do that is through something called a phase transition. So I'm just going to get my pointer here. So for a phase transition, say if we want to go from a solid to a liquid, like we talked about with the ice cube, we would have to melt it. To get back, we'd have to either solidify that water and freeze it, or solidify it. The same process to go from a liquid to a gas, we would either have to boil the water or boil the liquid that we have through a process called evaporation. And if we wanted to get it back to the liquid state, we'd have to condense it. The solid to gas is a little bit funny. You don't tend to see it as often in nature, but in fact, one of the examples you can see usually is on your car windshield. So on your car windshield in the winter, you'll often notice that there's frost on top of the windshield. And even though it hasn't snowed, it hasn't rained, it hasn't done anything, there's just frost on the windshield. And that's because water in the gaseous state desublimates onto the cold surface of your car and becomes frozen ice. And we can also make it go the other way by sublimating. So that's when we heat up that solid really quickly and it goes just straight to the gaseous phase. So that's how so those are our three states of matter and how we can move from each of them. And Samantha asked a really good question that asks, why does that happen? So they asked, why does heat make molecules move further apart? So just so you know, I'm using molecules and atoms kind of interchangeably. So atoms are just atoms are the building blocks that our matter is made up of, and molecules are different atoms that are stuck together to make a bigger building block. So Samantha asked, why does heat make molecules move further apart? And heat, you can think about it like the transferring of energy. So if we look at this piece of metal here, you can see when it's cold, the atoms are only wiggling around a little bit. But as we increase the temperatures, we increase the heat, we're adding energy to the system, and those atoms are starting to wiggle around each other even more. So I like to think about this just like when I'm tired, I don't really want to do anything. I just want to sit and be lazy on the couch. But as soon as I get some of that energy, I'm happy to move around and run and walk and do all kinds of things. So that's kind of what the atoms are doing here when we add energy to the system or when we heat the system. And what's kind of cool is that temperature is the thing that we measure to tell us about how much of this wiggle energy the atoms and molecules have. So for example, if we were to measure the temperature of this system, we'd measure that it's hot, which means that it has a lot of heat. And so heat is the transfer of energy, and there's a couple of ways that we can use the transfer of energy in our everyday lives to change phases from one to the other. So you would say change an ice cube to water on our stove by turning on the elements to heat it up. So that's where we are transferring energy from heat, or due to heat, but we can also do it in a different way. So here I have and this is a cool experiment that you can try at home. I did this in my backyard. So here I have a plastic pop bottle that I put just a little bit of rubbing alcohol in. And then on top here, there's some green silly putty that we'll talk about silly putty a little bit later. But what's important is that I put a little bit of rubbing alcohol inside of this pop bottle, and I've rotated it around so it coats the inside. And what's cool is that we're going to use pressure instead of temperature to change the state of matter. So what I have here is a plastic water bottle, and you can see again that I'm going to be putting this plastic silly putty ring onto it, just like this. And out of frame here I have a bicycle pump, and the reason I'm using silly putty is so I can get a good seal, so I can put pressure into the chamber. So I'm putting oxygen and nitrogen from our air into the bottle, and what that's going to cause, so you can't hear it right now, but it's going to so just to talk about this a little bit, when I'm putting pressure into the chamber, I'm actually adding molecules and atoms into that bottle. And what that's causing is the alcohol molecules to force up into the gaseous stage. So we can't see anything right now because it's in the gaseous phase, but there's gaseous alcohol molecules floating around in there. And if I keep going with this video, what you'll be able to see is when I take the pressure out, when I relieve the pressure, we see this puff of white. And what that is all those gaseous water or alcohol molecules are condensing. So we've changed from the gaseous phase to the liquid state, and they're condensing into these tiny little droplets inside of that bottle. So this is exactly the same process that we use, that clouds are formed in our atmosphere. So you're making a tiny little alcohol cloud inside of this bottle. And you can see I'm going to puff out some of this condensed alcohol out of the bottle. So that's one way that you can change state of matter, by using pressure instead of temperature, like we commonly think of. Okay, so now since we're talking about changing the phase of matter, so Thomas asked, what is the freezing point for oxygen? And Nash asked, why do different liquids have different boiling points? And these are good questions that actually tie really closely with each other. So there's oxygen in the air, and that's what we breathe, and we need that to stay alive. And at the standard pressure and temperature that we have here on Earth, that we live with, it's in the gas. Oxygen is in the gaseous phase. If we wanted to make liquid oxygen, one way that we can make it is by cooling it all the way down to negative 182.9 degrees Celsius. So it has to get really, really cold before we can make it into a liquid. So before we can condense that gaseous oxygen into a liquid oxygen. And if we wanted to freeze oxygen, we'd have to bring it down to even colder temperatures, which is negative 218.4 degrees Celsius. What I want to talk about is that to get liquid oxygen, it has to be really cold. It's only about 50 degrees above absolute zero. And we'll talk a little bit about absolute zero later on in this talk. And Nash asked, why do different liquids have different boiling points? So in the case of oxygen, for instance, the boiling point is going to be negative 182.9 degrees Celsius, where, say, for instance, water, the boiling point is 100 degrees Celsius. And we can think about this like, we can think about this going back to the idea of energy. So in order to have energy, or in order to make a liquid go to a gas, we have to break up those molecules and atoms. And the only way that we can break them apart from each other is by adding energies to actually physically make one atom not be next to the other one. And this is really easy for something like oxygen, which doesn't really want to be next to other oxygens. We have an O2 oxygen 2, so that means that they're bound together as two oxygens, but they don't really want to be next to any other oxygens. Water, on the other hand, has really, really strong bonds. Water likes to be next to itself. Water likes to condense and be a liquid at room temperature, which is why we can drink water. So for liquids to have different boiling points, it depends on how those intermolecular or interatom interactions, how strong those are. So for oxygen, it's pretty weak, and for water, it's pretty high. So they're pretty strong bonds for water. So, and since we're talking about moving between different states of matter, Megan asked, is there anything that is in between the three states of matter? And this is a question that's near and dear to my heart, because this is the field of science that I study, and it's called soft matter science. And I think we'll understand a little bit about why it's called soft matter with this example of silly putty. So I have a ball of silly putty, and I hope you all have balls of silly putty that you could play with at home too. So if I take this ball of silly putty and I drop it into my cup, you'll notice that it bounces around and it stays the shape of a ball. So that means it's acting like a solid. And you'll notice that it bounced around very quickly and it acted like a solid. However, if I leave that ball in that cup for a period of time, I'm showing a time lapse here of 30 minutes compressed into 30 seconds. And what I want you to see is that silly putty is moving, it's flowing, just like a liquid. And if I was more patient than just 30 minutes and I let it sit for a day, we would see that it covered the whole bottom of that cup, just like a liquid does. So, silly putty acts like both a solid and a liquid. And what matters is what time scale it's acting over. So over short time scales, it's acting like a solid, but over long time scales, it acts like a liquid. And that's really interesting. And we can understand why it acts that way by looking at the molecular structure of silly putty. So silly putty is a polymer. We have polymers all around us. Polymers make up plastics, polymers make up our DNA, polymers make up the structure of the trees that we see outside. But what I like to model polymers as are spaghetti noodles. So you can imagine that one molecule of polymer looks kind of like a really long spaghetti noodle. So if we have a ball of silly putty, it kind of looks like a whole bunch of spaghetti noodles tangled up in and around each other. Now you can imagine that on short time scales, if we put our fork into that spaghetti and we try to rip out a couple of noodles, we'd actually take all those noodles would get tangled up next to each other, and we take most of the spaghetti, that bowl, with us. So it doesn't have time to move and rearrange. We just take a whole chunk. So that's why it acts like a solid on short times, because the noodles get tangled next to each other. However, if I was to put my fork into that bowl of spaghetti and very slowly pull out just a couple of noodles, what I would see is that I would be able to come out with just a few of those noodles and no more than I had anticipated. And that's because I was very slow and careful, and I gave those noodles time to move and rearrange past each other. So the noodles are able to flow. And that's what's happening at long time scales. And so soft matter is kind of this interesting field that's halfway in between a solid and halfway in between a liquid. And I think it's my favorite, well, it's my favorite area of science to study. So we talked about soft things, but Emma asked, what makes diamonds the hardest material in nature? And what is the hardest manufactured material? So we all know that diamonds are very hard, but before we talk about diamonds, I just want to talk a little bit about what hardness is. And we're going to go back to a food example, because I think those are really, really fun. So if you imagine taking some crackers in your hand and putting them in the palm of your hand and taking your other hand and pressing down, what's going to happen? Those crackers are going to splinter and break into a whole bunch of little pieces, and then maybe you'll get in trouble for making a mess. However, if I was to take, so that it breaks up, it's very brittle. If I was to take a piece of cheese and do the same thing and squish it, maybe especially if the cheese was maybe left out at room temperature a little bit too long and it got kind of soft, and I was to press down on that cheese would just squish. And then maybe when I took my hand off, it would bounce back into the shape that it is. Hardness is a hard material is something that does neither of these. So it doesn't break when you press on it, and it doesn't squish and deform when you press on it. And diamonds are one of the most common, hardest naturally occurring materials that we have. And to understand that, why they're so hard, we need to look at how those atoms are rearranged. So diamond is made up of carbon. It's just made up of one carbon. So it's not a spaghetti noodle like the polymers were that I talked about earlier. You can imagine it more like just a ball. And diamonds have this really cool atomic structure, so crystal structure, where all the atoms are arranged equally around each other. And to understand why this is important, I want to take us to diamond's close friend, which is graphite. Now, we use graphite in our pencils to make notes and hopefully when you're doing math homework. But the atomic structure for graphite, although it's made up of carbon just like diamonds are, is that they're arranged in these sheets. So we have all these sheets of different carbon atoms that are lined up. And between these sheets, there's not a lot of bonds you can see that there's empty space between these. So there's very weak bonds between those sheets. And when you're writing, you're actually breaking those bonds and leaving behind carbon onto the surface of the paper. So so graphite is very weak in that sense. However, diamonds, you can see that every atom has 4 friends that it's connected to. And so when you press on this atom, or when you press on diamond, it gets all that stress, everything is distributed among each of them. So it's harder to break diamond because everyone takes care of each other. And Emma also asked, Emma, I just want to check. Emma also asked, what is something that's the hardest material? And the answer to this is kind of hard. So, so there's a material called lonsdaleite, and it's estimated that's going to be 60% harder than diamond. However, this has only been found in theoretical experiments. So people have only been able to predict that lonsdaleite is going to be harder than diamond. We haven't actually been able to make a sample in real life yet. We do see samples of lonsdaleite in nature. They think it's from where diamond deposits have been hit by a meteor, and that the pressure of the meteor is enough to change the shape of the crystal structure, which is, you can imagine that just thinking about that this material is very, very rare in nature. And the problem is that most of these samples that we see in nature, and most of the ones that we've made in the lab so far, aren't pure. So you can see even in this picture here of the sample, there's all these little inclusions, there's all these defects inside of that crystal. So we've only been able to think about this in theory. We haven't actually been able to make it in real life yet. So maybe one day we'll be able to understand how this works. And so to come up with the next couple of questions, Diego asked, why do teachers always focus on 3 states of matter? Where does the 4th, plasma, fit in? And in a similar sense, Thomas asked, what is the term for gases transforming into plasma, just like melt, evaporate, condense, freeze, and sublimate? And I'm guilty of only focusing on the 3 phases of matter too, so just like I did at the beginning. And to start off, plasma is the next step after gas. So plasma, you'll understand why I kind of drew it as these squiggles. I'm not the best artist. But plasma comes from giving more energy from gas to gas. So if you have very, very hot gas, what happens is that it can ionize, so the process is called ionization, and it will turn into a plasma. And to understand why that happens, we need to look a little bit closely at what atoms look like. So I've talked about atoms, and I've just mentioned them, they're kind of like these little balls that ping around in our when they're in the gaseous state. But if we were to look at a nucleus, even closer at an atom, we see that we have a positive nucleus that has protons in it, so it's positively charged, and we have negatively charged electrons, as we can see here. And if we add heat or energy to this atom, what we can actually do is cause the positively charged nucleus and the negatively charged electrons to move away. So we're splitting up the positive and the negative charge. And what happens then is that this turns plasma into something that used to be very insulating, so it wasn't able to conduct electricity very well because it was neutral, so everything here is neutral. But here, we have all these charges that are able to move around, and that allows electricity to conduct very well. So one of the characteristics of plasma is that it's able to conduct electricity very, very, very well. And I'll show you some examples of this in a second. But before we do that, I just want to talk about if we wanted to make plasma back into a gas, and that's a process known as recombination. So we take out some energy from our system and we become a gas, or we become back to a gas that's neutrally charged. Now, to come up with some examples, we saw them if you live in Southern Ontario, we saw them last night. So one of the examples is lightning. So much energy is stored up in the atmosphere that it has to find a way to discharge it. And through discharging it, it creates a plasma that allows electricity to conduct from the atmosphere to the ground. So lightning is a plasma. And in fact, you can do this on a very, very small scale at home in the winter. So if you have carpet and you shuffle your sock feet on the ground, and then you try and go and zap one of your siblings or your mom, or the couch zaps you, something like that, that discharge, you just made a plasma. We also make it pretty common, and more common than we expect, because we see that in neon lights. So in this case, we're charging up the gas inside of the neon lights using an electric field. And we also plasma is also present in stars. So here's a picture of our sun here, and it's also present in all the other stars because these are systems with so much high energy, and it's all made out of gas, and that energy causes a plasma to be made inside of the star. And so we talked about, so this is on the very, very hot scale. So I want to talk a little bit about what about if we go the other way? What happens if we make it very, very cold? So Leandro asked, what is absolute zero? And Carlos asked, what would happen if you cooled something to absolute zero? So absolute zero is defined as 0 Kelvin, or negative 273.15 degrees Celsius. This is really, really cold. And this means that atoms have no more thermal energy. They're not moving around at all. They're not wiggling. They're not turning. But it doesn't mean that the system has zero energy, because even when we get really, really, really low and to really cold temperatures, atoms still have energy because of quantum mechanics fluctuations. So it gets a little complicated, but essentially, if you have an atom and you try and confine it to a certain spot, in turn, there's an uncertainty principle called Heisenberg's uncertainty principle. That means that if we confine the position, we also can't confine the momentum, so the movement of the atom. So there's always going to be energy associated with it, is what I'm trying to say. And it gets that's what scientists are looking at right now, because that's when we can actually measure quantum mechanics. So by cooling things down, so we take out all the thermal noise. However, Carlos, you asked, we can't get to absolute zero. What happens if we get to absolute zero? And we actually can't get there, because just like when it's cold out in the winter and you put your warm hand on the cold window and you can feel your hand getting colder, we're transferring heat from our hand to the window. And this is exactly what happens whenever we are trying to get close to absolute zero. If we have anything at all around it, any atom, anything with any sort of temperature or heat associated with it, it will go and cool down the matter that we're trying to cool. So it's kind of this backwards loop of the more we cool it, the more heat we transfer to it. However, we can get really, really, really close to absolute zero. So on the International Space Station a couple of years ago, atoms were able to be cooled to 1 picokelvin. So millionth of a Kelvin. If I were to draw a line here, it would still be above that. It's so, so, so cold. And that's when they can do really, really, really cool experiments with quantum mechanics. And they can look at, for instance, Bose-Einstein condensates, which I think you might be learning about next week. Okay, so that's what happens if they're really, really cold. And I think the final question to finish off today's webinar is, Will asked, is it possible that there are more elements in the universe that haven't been discovered yet? So we're all familiar with the periodic table. So we define atom or different elements as the number of protons that are in a nucleus. So for instance, a hydrogen has 1 proton. We can go up to silver, which has 47 protons. And we can't split a proton in half. We always have to have an integer number of protons. So the only way that we can make new elements that we haven't discovered yet is by adding on more elements. So we could say, so the next element that we could try to discover is number 119, which would actually be over here on the periodic table. So the only way that we can do that, and so all of these atoms here that are made, or elements here that are made here, have a they're very unstable. So as soon as we make them, they break apart almost instantaneously. Just enough time for us to measure them, actually. So the way that we can do that is in these big labs. So for example, Berkeley Lab in the United States focuses on making new elements. And one of the things and the way that you do that is by taking 2 smaller stable elements. So for example, we could take something like gold, and we could smash those 2 gold together, and we would hope that those protons would stick together, and then whatever is left over has a higher atomic number, so more protons than 118. And in that case, then we've made a new element. So that's how we can make new elements. So it's possible that they're out there, but they wouldn't last very long because they're very big and very unstable. And so that finishes my talk. Thanks for watching Ask a Scientist. I hope you guys learned something today that you can take home, and maybe some experiments you can try at home as well. And I hope you keep learning and stay curious. Thank you.